everyone. We would like to open it up now for the Q&A. Again, please drop questions in the Q&A box below. We do have some questions that have come in already. Let me start with that. Okay, Ming, do you do wafer or module level burn-in? And is that required for SiC MOSFETs?
Yeah, very good question. So to ensure the quality of our devices, which means low failure rate, we do die level burn-in. For example, we stress the gate oxide before we ship them, and then we screen the devices after a certain stress to make sure that the weak dies are not going to be shipped to our customers. And that also means we have a much lower failure rate in the customer's hands. So there is a bathtub curve in the in typical products life cycle. You will see a higher failure rate at the beginning, and we use the burn-in process to basically eliminate those early failures.
Okay, thank you. All right. Let's see here. Is there no plan for 900-volt rated devices?
Unfortunately, I think 900 volt is not our focus at this time. We believe most applications can be addressed by either our 750 volt or 1200 volt class. And there are some higher voltage applications, for example, PV application that might need higher than 1200 volt. So we are looking at that, for example, 2000 volt to develop a new voltage class, but 900 volt, not at this time.
Okay. How do you address reliability issues called the body diode degradation that results in on-state resistance increase of metal oxide semiconductor field effect transistors, MOSFETs, that can be triggered by current flowing through the body diode when it is forward biased?
Yeah, very good question. So we understand the body diode can suffer from bipolar degradation, which is caused by some defects, basal plane defects in the material. So we do ensure the body diode is tested and make sure that the degradation will not occur. So we do test both pulse test up to the rated current and continuous current test. We probably will not be able to do continuous current test at the full current because body diode of silicon carbide has a high on-state voltage, which means it will get very hot if you run at the rated current. But we do the pulse test at full current and continuous test at lower current to make sure there's no bad degradation that will happen in the devices we ship.
Okay. A few more that have come in. Do you offer half-bridge SiC FET and or GaN FET modules?
Okay, so for silicon carbide, let me get back to one of the slides here. So we do offer silicon carbide half-bridge modules. For example, this DOT247 that looks like a discrete device is actually a half-bridge module offered at 750 volt and 1200 volt, up to 150 amp rating. So this one is a half-bridge module. If you want even higher current, then all these high power modules, the case type and TRC drive pack, they are half-bridge modules, more than 300 amp capability. For GaN, although we didn't cover it in this presentation, we do develop GaN devices and also modules. I can briefly talk about it. We offer 150 volt and 650 volt GaN devices, and we also develop modules. It's not currently on sale, but we are developing half-bridge modules integrating two GaN HEMT and the gate driver for both voltage class, 150 volt and 650 volt in QFN package.
Okay. Are you planning to have SMT, the top side cooled
Topside,
package,
yeah.
tolt type.
We do, yeah. We do. We are planning to offer a surface mount topside cooled package that is similar to what's available on the market. So we have been investigating the trend of discrete devices, and we know the, for example, for onboard chargers and similar applications, there's a trend for customers to prefer surface mount device with a better heat heat sink attachment. So topside cooled package, for example, compared to ST's package. Uh, we understand that that is a trend, so we are developing something that is similar. But we do see there's a problem with currently available packages on the market. So because we offer silicon carbide devices in two voltage classes, 750 volt and 1200 volt, um, the existing packages we see on the market, they are really only good for the lower voltage class. For 1200 volt class, for example, if you have a DC system voltage of 800 volt, 900 volt, then the creepage distance for that package is not sufficient. So we are trying to solve that issue before we release the product to the market. So that same product can be used for both 750 volt and 1200 volt class products. So yes, in case if you visit our booth in APAC, we actually will bring a sample, early sample of our topside cooled package, uh, just to show you our idea.
And some more questions coming in here. Your Gen 4 SiC MOSFET gate voltage recommendation is 18 volt -OV. If we drive it at 15 volt, is there significant impact on the reliability performance?
There's no negative impact. In fact, is if anything, theoretically, you have a positive, a favorable impact because you are driving the gate uh, with a milder voltage. So the gate overdrive is less, which means probably the reliability will be even better. The only sacrifice is a slightly higher conduction loss. Like I showed in the previous slide, it's about 10% higher conduction loss. If you can handle that, then 15 volt drive is no problem.
Okay, thank you. Let's see here. Recently, SiC is getting more adoption into EV powertrains, but there is also strong competition from silicon IGBTs that are much cheaper. Do you expect SiC to come down in cost and fully replace IGBT for traction applications?
Yeah, very interesting question. So we all know silicon carbide will have better efficiency than IGBTs, but I don't expect silicon carbide's cost to come down to really compete with IGBT for the same rating. It will always be better in terms of efficiency, but not in terms of cost. So IGBT could be a good baseline solution for many EV applications. For example, hybrid vehicles. You do sacrifice some of the losses, but even if you change that to silicon carbide, improve, let's say 10% of the energy consumption, there's not too much battery cost to save to pay for the additional costs in silicon carbide. So I don't think all electrified vehicles will in the foreseeable future need silicon carbide. Some will still be very good with IGBT inverters. But for battery electric vehicles, in many cases, or maybe in most cases, uh, with the new silicon carbide prices coming down, you would see a benefit of adopting silicon carbide, improving the efficiency and reducing the cost in the battery for the same drive range. But that's assuming if you either use an IGBT inverter or a silicon carbide inverter. Does it have to be 100% IGBT versus 100% silicon carbide? That's something the industry is debating and thinking about. I think there may be a balanced point where you can take advantage of both IGBTs and silicon carbide in the same vehicle.
Do you make your own die, and can you provide the die only?
Yeah, of course. So we actually we do substrate, device wafers, bare dies, packaged products, and we can support customers on all levels. We can sell substrates to device makers. We can sell bare dies to module makers. We can sell packaged products for system makers. So yeah, because we are vertically integrated and we are glad to support all level of customers. So simple answer is yes, you can buy bare die from us.
Thank you. Let's see here. Okay, we have another question come in here as well. Let's see. Thanks for sharing ROHM's SiC product information. I see that you are developing many new packages for automotive inverters and battery charges with up to 1200 volt rating. Do you also offer high voltage SiC MOSFETs that are suitable for applications like high power solar energy conversion?
I think I covered this a little bit in the previous question, but let me repeat. So we do understand the solar industry is probably moving to higher voltage, like 15 volt, no, 1500 volt DC voltage, and that would require a higher voltage device, not 1200 volt. So we currently offer 1700 volt silicon carbide MOSFET with Gen 2 technology, planar gate. So that's relatively older technology, still usable, but not the latest. We will develop Gen 4 higher voltage. We plan to offer 2000 volt class Gen 4 silicon carbide MOSFET in the near future. So we can probably share more details next year when we have more development results available.
Okay, there's another question that just came in. What is the maximum junction temperature of ROHM's SiC MOSFETs? And can they operate at a higher temperature than 175 Celsius?
So for our standard product, like the discrete product, we rate the device at 175 degrees C. But the die itself can support limited duration at higher temperature. So in our power modules for automotive traction use, we actually rate the die and also the module at up to 200 degrees C for 100 hours. There's a assumed mission profile associated with this higher temperature capability. So it's not you can use 200 degrees C forever, but under common a representative mission profile, you could use above 175 degrees C for up to 100 hours with our Gen 4 technology.
All right, another one just popped in. Let's see. Do you plan on adding a module similar to EasyPack modules to your portfolio?
At this time, we don't plan to make EasyPack module. We have some other modules that could replace that with more compact form factor. For example, the HS-DIP module. Um, this actually is a higher level of integration. This package support 4-in-1 or 6-in-1, and at a power level that you can typically also use a EasyPack module. So although it's not compatible, if you are open to a redesign, this package might be able to save you a lot of board space.
I just want to let everyone know that this presentation will be available on the on-demand landing page after the webinar, which we will share with you. Thank you for your time today. We hope you'll join us again for future webinars.